Hello everyone, in this series I'm going to show you how and why gradient descent works. And by the end, we will have coded our own neural network class from scratch. Gradient descent is an algorithm that is at the core of most machine learning models, and no matter what you're doing, it'll always come in handy. If you're just starting machine learning, this is a must-know. However, it is also very intimidating. I know when I first set out to learn about gradient descent, I got scared and relied on libraries to do the work for me, but that made me lose the key understanding of the algorithm that resulted in a lot of Stack Overflow and slow progress. In reality, it's not that bad. Even though the notation looks scary, if you give it a shot, it all starts to make sense. So let's get started. In this video, we will set up everything we need to approach gradient descent. We will start off simple with feed-forward neural networks. So the idea of feed-forward neural networks is very closely related to how our brains work. We have layers of neurons, and each layer connects to a layer ahead of it. The first layer is called the input layer, the middle layers are called the hidden layers, and the output layer and the last layer is called the output layer. We define AL sub j as a number corresponding to the activation or output of the jth neuron in layer L. So for example, if we look at the second neuron in the first layer, that would be A1 sub 2. We define BL sub j as a number corresponding to the bias quantity, which we'll talk about later, of the jth neuron in layer L, similar to how we defined A. And finally, we define WL sub jk as a number corresponding to the weight connecting the jth neuron in layer L with the kth neuron in layer L minus 1. So for example, the weight connecting A1 sub 3 and A2 sub 2 would be W1 sub 2 3. Now you might be wondering why we chose to make the subscript of W start with the 2, even though 2 is the index of the neuron at the end of the connection. Isn't this a little weird? Don't worry, this will become clear in a moment. It simply helps make the math and efficiency better. You can almost see the connection this has to our brains. The activation is kind of like how strongly a neuron fires in the brain. The weight represents the strength of a connection between two neurons, and the bias acts as a threshold value that the other components of a neuron needs to pass. Using what we have so far to determine the activation of a neuron, we could simply sum up the product of the activations in the previous layer and the weights connecting them, and then add the bias at the end. And this would match our brain interpretation of neural networks. We call the value we just obtained ZL sub j. For us, that would make Z2 sub 2 become the following: the product of these two terms plus the product of these two plus the product of these two, and all with the bias summed at the end. One idea to get to the activation, AL sub j, is see whether Z is positive or negative, and then let A be 1 or 0 based on that. And if you did that, you would have the first model of a neuron ever created, the perceptron. You can see how the activation would look based off of Z in this graph. It is just part of the step function. However, gradient descent is based on observing small changes to neurons and seeing the small changes in the output that result from this. If we look at our step function, small changes to the input can completely change the output of a neuron. So for this reason, to get to our output, we use a smoothened out continuous version of the step function, the sigmoid function. Now, although this equation might look a little daunting if you haven't seen it before, once you graph it, it becomes clear that it really is just a smoothened out version of the step function. With that out of the way, we can finally define AL sub j, the activation of the next layer, by applying the sigmoid function to Z. And then after that, there's one last improvement we can make. Instead of using AL sub j, BL sub j, ZL sub j, and WL sub jk, which is already a mouthful to say, and a lot of math to write down, we use a bit of basic linear algebra to simplify. Define AL as a vector containing all the values of AL sub j, and then define B and Z similarly. This is going to get you these equalities here. Notice that they're all column vectors. For the weights, it's a bit more involved. Do you remember how we indexed W with JK, where K referenced the previous layer neuron and J referenced the neuron afterwards? We did this so that we could define W as a matrix containing J rows and K columns, making a J by K matrix. And this equality shows you what the weight matrix looks like. And when everything is defined like this, the equations become really nice and compact. Take a moment to let these two equations sink in and see if it all makes sense. To help make this idea concrete, I will show an example. Take a look at this neural network right here. We will calculate the question marks, which are the activations of the last layer. We can write out the values of A0, B1, and W1 using the information we already have. After that, we can apply our first equation to get ZL, or Z1 in our case. And then once we have Z1, we just need to use our second equation and apply the sigmoid function to it to get A1. And this is the activations of the last layer. Great! Now with all this theory behind us, we can finally write out the code for the neural network. We start by taking in a list containing the number of neurons in each layer. Since the inputs to our activation function can vary, the only invariants are really the weights and the biases, and that is why our neural network class only keeps track of those two. To initialize our weights, we use numpy.random.randn, which initializes values according to a normal Gaussian distribution. Now, if you don't know what that is, this graph shows you what it looks like. The y values vaguely represent the probabilities the x values get picked. By initializing them like this, we just make sure they don't become too big and take over. Self.bias becomes a list of all the bias vectors, and each vector has shape x, 1 to make it a column vector with x variables. Self.weights uses that, so to speak, backwards indexing and becomes a y by x matrix. One important thing to notice is that the length of self.bias and self.weights is going to be 1 less than the length of layers, or 1 less than the number of activation layers we have. And this is because we don't keep track of biases in the input layers. And for the weights, since they're connections between layers, they also have this property. Finally, to pass information forward, we create a feed-forward method, where what we do is we implicitly calculate z in this expression right here. And then once we implicitly have z, we apply the sigmoid function to it to get the next a. And then we keep on going until we get to the last layer. We can check if this works by testing this on our previous example. After setting the biases and the weights, we get the activations to be this. And this matches with what we had before. Great! That's it for this video. In the next video, we will tackle gradient descent head on. If you learned something from this video and are feeling especially activated and have a bias towards this video, please help me out and like and subscribe. Thanks for watching.